Hey, thanks for watching this video. This is one class from the 2022 HVACR Symposium in Claremont, Florida. We have the symposium every year, and so to find out more information kind of upcoming, go to hvacrschool.com/symposium. Big thanks to our sponsors for this event, which was AccuTools and TrueTech Tools. They're the two title sponsors that made the event possible. In this great session, Rick Streacker talks about the impact of static pressure on fan and blower motors.
Appreciate everybody being here. I want to thank Brian and his team for doing this. I know a lot of you guys have come a little bit of a distance to participate in this, but I think it's a great event for all of us. So again, my name is Rick Streacker. I'm out of Georgia, and I started out in the motor shop in 1969 in Dayton, Ohio, and I worked for Fasco and also A.O. Smith before going to work for Packard. So the impact of static pressure on fan and blowers. Well, that's easy. That's easy stuff. I think first of all, let's take a look at the refrigeration cycle. Because when we look at the refrigeration cycle, we can see where the fans and blowers come into play. When we look at this cycle, what those fans and blowers are doing are helping us move air over our coils in order to make that refrigerant more effective in our heat transfer. So we use fans on the condensing units. How about on the evaporator side? Do we use fans or do we use blowers in refrigeration? Fans or blowers in refrigeration? Fans. But don't we use blowers in HVAC? So we use fans on the condenser side for both the refrigeration and HVAC applications with condensers, but we use fans in refrigeration and blowers in HVAC. Why is that? Why don't we use fans for everything? Wouldn't that make things a little bit easier? Why don't we use fans in heating and air? Because we're moving that air a much greater distance, aren't we? So we're taking that air from maybe an area over here in our living area and moving it way across the house. And how do we get that there? We go through ducts. Now what do those ducts do? What does that do to our airflow? It helps restrict the airflow, doesn't it? So the air doesn't want to move through those things. The ducts don't want the air to move through there. And so in order to get the air all the way over there, we have to pressurize it. And that's what a blower does. That blower is going to pressurize that air. It'll squeeze it down and move it, help us to move that air greater distances than we can with the fan blade. The fan blade isn't able to effectively move it through those ducts because of the static pressure. So we use axial fans. Has anybody heard that term before? Axial? What is an axial fan? Chris, you know what an axial fan is. Propeller blade. So it looks like this. Now we call it an axial fan because that fan blade, it's turning around an axis, and it's moving the air around an axis. And it pulls air from one side of that fan blade and pushes it through the other side of that fan blade and provides more force, more pressure through that as it's moving. That's an axial fan. So when we look at a fan blade, this is on a refrigeration application. It's taking the air, bringing the air in from one side, pushing it through the other side. Now, when we look at an axial fan is affected by static pressure. Its performance is affected by static pressure. So free air with the static pressure on the fan blade results in the least loading on that motor. Does that make sense? If it's free air? What would be free air? If I were operating a motor with a fan blade on it, and if I'm running it on this table here, this is considered free air. That would be the least load on that motor. But now as I add static pressure, how would I add static pressure to that? Put it in my condensing unit. So I put that in the condensing unit. What if I put it in the condensing unit but don't put the guard on top of it? Have I added static pressure to that? Yeah. What if I put the guard on it now? Does that change the amount of static pressure I've applied to that? And it does. So as I add static pressure to that, what does that do to the load? It increases the load. And if I have a PSC motor, what might that do to the speed of that motor as I add static? It would slow it down as I add static. As I add load to it, it would slow it down. What would happen to the amps on a PSC as I add load, as I add static? What would the amps on the motor do? They would go up. That makes sense, doesn't it? Does anybody disagree with that? No, that makes sense. If we were to look at a fan catalog page, if we look at that particular catalog page, we can see certain performance characteristics of that. Now, one thing that's not shown on that is the effective static pressure. As I move from the left to the right, that's an increase of static pressure. And that would result in changes of my air. It would change the impact on the performance of that fan as well. But as I add static pressure to that, it's going to increase the load on the fan blade. Now, if I have a residential condensing unit, typically I might see about 0.3 inches of static, maybe a little more static on a commercial unit. Who checks the static pressure on the condensing unit? Is there anybody who does? Not you, Eric. You check everything, Eric. But probably you don't check that. But you can visibly look at that condensing unit. If you see the amps are high on the condensing unit, and you see that the coil is dirty, or if you've just mown the lawn and you have grass clippings all over that, you can probably associate that there's probably more load on the motor, that your amps on the motor are going to be a little bit higher. That's pretty intuitive. That kind of makes sense. So if I look at this, that unit, is there anything that might impact the static pressure? No problems with that, right? Is there anything that would impact the static pressure on that? Yeah. And if it's pretty close to the wall, that could impact my static pressure as well. And I like how we have those connections right up there. That's nice and convenient for the kids to play with. So, but that, as we add static to that, that's going to put more load on this. It's going to result in less air too. How about that? And look how close those units are. And that's going to affect my static. It's going to affect the amount of air that I have on that. And I could see an increase in my amps as a result, and again, a reduction of air. And these are things that you typically run across. That stuff happens. If somebody has a deck built over their condensing unit, and if they have a trap door on that deck, if you were to measure the amps of the motor with the trap door on, with the trap door off, that's going to affect that static pressure, which is going to affect the load, which is going to affect the amps on that motor. So those things all affect static pressure and the load that I see on that. How about that? Anybody ever run into anything like that? So what's that going to do to the amps on the motor? Cause them to go up. What would that do to the operating temperature of the motor? It would increase it. What would that do to the speed of the motor? Slow it down a little bit. So when we think about load, it's going to impact the performance of that motor. And if I increase the load, the motor's probably going to slow down a little bit. If it slows down a little bit, I could probably see that I've increased the load just by looking at my amps on that. And my amps would go up. What about centrifugal fans? What are centrifugal fans? Eric, be quiet. What are centrifugal fans? Don't say anything about, don't answer this. What are centrifugal fans? Blowers. They're called centrifugal fans, but we call them blowers. Centrifugal blowers, squirrel cage blowers. They look like this. If we look at these blowers, most of the blowers that we work with are that A, what we call a forward curve blower. That's the majority. We see some others. We see some backward curved or radial blowers, but most of the blowers that we see in our residential applications are going to be those forward curve blowers. Now with a forward curve blower, something a little bit different about them than with a fan, an axial fan. So with a forward curve blower, we bring air into the inlet of the blower. So that would be the inlet, that's the outlet of the blower. But we bring air into the inlet, and we do something different with that air than what we do with a fan, with an axial fan. Now, with that air coming into the inlet, we change the direction of the air. Typically, we change it by 90 degrees. So we bring the air into the inlet, we change the direction of it by 90 degrees, and we pressurize that air in the housing of the blower, and then we discharge that air. A little bit different function with that blower than with a fan. So does that have an impact on anything? Would that result in any different impact with static pressure? Does static pressure affect a blower the same way that it affects an axial fan, a fan blade? Does it? So let's say that I take the blower out of my furnace and I put it on the table. Is this considered free air, low static, or would this be considered high static? Low static, free air, low static. Now, when I run that blower on the table with no static on it, would I expect that that blower is going to operate at a lower amp range or a higher amp range than maybe its nameplate amps? Higher. Well, when I ran that fan blade in free air, weren't my amps low, the least load on it? So I'm trying to do more work. Now what that blower is doing, it's taking the air that is available to it, and if I'm running it in here, it has all this air that is available to it. And it's trying to take all of this air into its little inlet, change the direction of it, and pressurize that air. That thing's going to work as hard as it can. What would I expect to happen to that blower operating in that condition? What would the motor reaction be? May go out on the overload protector. And that motor's probably going to run a little bit slower than what it's operating speed is designed for. And what would the amps look like? Really high. Really high amps. Now I take that blower and I put it back in the furnace. I don't put the doors on there, and the furnace doesn't have a filter in it. When I put the blower back in that furnace and operate it, have I changed the static pressure? What have I done to the static pressure? Have I increased it or have I decreased it? I've increased it because it was free air here, zero static. So now I've increased the static pressure. I've increased static pressure. Does that increase the load on the blower? It decreases? Well, why is that? Why would it decrease? So now what I've done is I've restricted the amount of work that that blower is going to do. You know, a wise man, I heard a guy talk about this one time. I thought it was a great description of what was going on. If we look at that blower is designed for a certain amount of work. How do they identify the amount of work that the blower's supposed to be doing? There's a measurement that we use for that, CFM, cubic feet per minute. Now, I like to think of the load on that blower as boxes of air. Boxes of air, 1 foot by 1 foot by 1 foot, a cubic foot. Now, if my motor, I'm looking at this from the perspective of an air-over motor right now, and we want to keep this in mind. But that motor, let's say that it's a 1/2 horsepower motor. It's designed to move a 1/2 horsepower of these boxes of air. How many boxes of air is that? I'm not smart enough to know that. I don't know how many boxes of air it is. But I do know that if I have restriction to my air on my system, and if my system's designed for that 1/2 horsepower motor, I'm supposed to have 1/2 horsepower of these. But if I put restrictions on it, it's going to reduce the amount of air that it sees. So the number of boxes of air that it was doing on this table is going to be greater than the number of boxes of air it's going to do in my furnace with the door off. Now remember, I've got the filter off of there right now. If I put the door back on the furnace, does that change my static pressure? If it changes the static pressure, does it increase it or decrease it? It increases the static pressure. So if it increases the static pressure, what will that do to the load? Less load. Now wait, does this stuff make any sense? That's not what we saw with the fan blade. As I increased the static pressure with a fan blade, it increased the load on that. But as I increase the static pressure on a blower, remember what I'm doing. I'm restricting the amount of air. So I have less of those boxes of air. And if I have less boxes of air, I have less load. So now I put the door on the furnace. I'm restricting more air. My increase in static pressure is affecting that. My motor will speed up a little bit if that's a PSC motor. What will the amps do? Well, if it speeds up, it's working harder, right? No. It's speeding up not because that motor is designed to go faster, but as I put load on it, or I take load away, that's going to affect the speed of that. So now as I take load away, because I'm restricting the air, the motor goes a little bit faster, and I may be able to hear that. What will the amps do? They drop. Okay, let's look at something else here. I didn't have the filter in there. When I put the filter in, will that affect my static pressure? what will it do to the static pressure? It'll increase it. So if it increases the static pressure, what does that do to the load of the motor? It decreases it. I'm restricting air. So the motor may go a little faster. What will the amps do? They drop. Okay. Now let's assume that my filter is dirty. Dirty's bad, isn't it? A dirty filter is bad. Does that affect the static pressure? What will it do to the static pressure? Increase it. So what does that do to the load on the motor? Dirty filters. Does that make the motor work harder? Not on a blower. It's restricting more air. So there's even less load on that. Motor will go a little faster. What will the amps do? Drop. We love low amps, right? Are low amps good? Not necessarily. So on these motors, the motors that are designed for our air-moving equipment, they are designed for really a specific load. And that load, there's a narrow operating window in there. And if I'm trying to operate a motor on my air-over motors outside of that range, I might have a little bit of a problem. And the motor could be too strong. It can also be too weak. And we recognize if a motor is too weak, real high amps. But if the motor is too strong, my amps are going to be real low. Now, if I've got a motor that is too strong for the application, or if I don't have enough load on it because of static pressure, that changes my airflow, doesn't it? It restricts airflow. So now, if that motor is operating with too little load on it, what's going to happen? The motor's going to operate inefficiently. And if it operates inefficiently, what will that do to the winding temperature of the motor? It'll increase it. Even if my amps are low? Yeah. So now I've got real low amps, but the motor's operating inefficiently. That means the winding temperature increases, but I have less load than what the motor is designed for when it's operating efficiently. So what will happen to the life of the motor? You're going to shorten the life of the motor. And as a rule of thumb, if you change the winding temperature of a motor by 10 degrees C, 18 degrees F, you affect the life of the motor by what percentage would you guess? 50%. 50%. Now let's say that I do have dirty filters and that motor doesn't have as much load on it. Will it affect anything else in my system besides the motor? Think it could affect the capacitor? What might it do to the capacitor? If that motor is operating at a higher speed than what it's designed for, my capacitor volts increase. So if my capacitor volts increase, and if they exceed the rating of the capacitor, what do you think it does to the life of the capacitor? Shortens the life of the capacitor. There's a whole effect with that thing. So now when we look at blowers versus fans, the static pressure affects it differently, in just the opposite manner. So with blowers, free air is the maximum loading, and my amps are going to be high at that point. But as I add static, it restricts air. It restricts the number of those boxes of air that blower is working, and less air then takes load off of that. And my amps will drop. the speed will increase with that. Does it make a difference if I check the amps with the door off of the furnace? And why does it affect that? Yeah, it changes my static, which impacts the load, the number of those boxes of air. And so as I measure that outside of the conditions that it's designed for, I could be seeing numbers that don't really reflect what's going on with that particular product. So I always have to make sure everything is in place when I check the amps. Make sure all the doors, panels, filters, guards, if that condensing unit is under the deck and there's a trap door to access it, you've got to make sure all of those things are in place when you're checking the amps of that motor to make sure whether it's operating properly or not. So those are important characteristics to consider. Now this happens to be a blower chart. It's a complete blower. But you guys change a lot of blower wheels, don't you? So you'll go out and just buy a replacement for the blower wheel and keep the housing that's in there. Have you ever asked the guy at the counter, what CFM is that blower wheel? Anybody ever asked the counter guy that? If you do, he's going to give you the same answer I give you. I don't know. I don't know what the CFM of that is until I match that with the housing. So until it's matched with the housing, I really can't tell you what the performance of that's going to be. But when we select those replacement wheels, we select them so they have the same physical characteristics as the blower that was in there. And then when we put that in the housing of that blower, we expect that it's going to be similar in performance. Now, if we look at this chart, and if we look at this blower, the very bottom row, and look all the way at the right, in this catalog, we identified that blower as 1,000 CFM. So if you go into the wholesaler and you want 1,000 CFM blower, that may be what they give you. But more than likely, if you need 1,000 CFM in your application, and if you put that blower in there, you're not going to get 1,000 CFM. Why not? Because when you install that blower into an application, now you're going to introduce static pressure. And when you introduce static pressure, you're going to restrict air. And let's say that I have an application requiring 0.4 inches of water column. Well, now all of a sudden, I'm only getting 850. That happens to be a 2-speed blower. That's why we see 2 different numbers in there. But if I'm operating this on high with 0.4 inches of static, the air I'm going to get is 850 CFM. So if you need 1,000 CFM at 0.4 inches, you need to let the wholesaler know that that's what you need in order to get the right one. So we have to look at the performance we need at specific static pressures. Typically on a furnace, we might see about 0.8 inches of static, but that will have static pressures from 0.4 up to about 0.8 generally with our static. Now these motors that we have in these applications, they're called air over motors. What does that imply? Air over. Yeah, it's the air, it's the load that it's applied to that's going to keep that motor from overheating. Now when we look at belt drive motors, for example, those motors cool themselves. And so they may react to static pressure in terms of their ability to handle it, a little bit differently than what I might see with an air over motor. But it's important to remember that in these applications, they're air over motors. So with that, what does that do to my static? And what does that do to the amps on my PSC motor? What? And one of the most difficult things, and this is difficult for me too, is to make sure that I'm telling you properly. This stuff, when we talk about blowers, to me, it's not intuitive. When I talk about fan blades, that all makes sense, and I can see it, and it looks sensible to me. But when I see that, I see trouble. And my natural tendency is to think, now my motor's going to be higher in amps. But it's not. It's still bad, but my amps are going to be real low. And what makes it so bad is now the motor is operating so inefficiently that I'm putting so much heat in there, but I'm not getting the airflow because I'm restricting air. That's where the problem comes in. So those low amps are a problem as well as high amps. So these are air over motors. So the condenser totally enclosed, the blower an open motor. Now what's going to be important to make sure, I had mentioned to you that we select these motors and they're designed to operate within a narrow window because they have to have the right load on them. If we don't have the right load on them, then that motor is going to overheat. And so we use a rule of thumb when we replace these. And the rule of thumb is that if this is the bad motor, my replacement motor should be equal to the amps of that motor, the nameplate amps, the FLA to that motor, but not more than 25% stronger. So that's identifying this window. Now, as a technician, what's critical for you is that once you select a replacement and you install it, that you check the amps of the motor and that you check the amps with everything in place. And then when you check the amps, this comes as a little bit of a surprise to folks. It's okay if the amps are a little bit higher than nameplate, but not more than 10% higher. As long as those amps aren't more than 10% higher than what the nameplate on that motor says, I've got the proper amount of load, the motor is operating in the right efficiency, I'm getting the right amount of heat in there, and I've got the proper amount of air, which is the load, helping to cool that motor. But then also, the amps should never be more than 25% below nameplate. If it's more than 25% below the nameplate amps, that's an indication it's too inefficient. I don't have enough load on there. I put more heat in the winding of the motor, and remember, the load is the air. So if I don't have the proper load on it, then that motor's not going to get the right amount of air to keep it from overheating. Now, Chris is really good at these products here. So when we look at electronically commutated motors, what do we call those? Do we call them variable speed? If you went to Chris's class, they're not all variable speed, are they? There are some that are, but they're not all variable speed. But what they are is air over motors. So these motors also are dependent upon having the proper load on them for them to operate for the longevity they're designed for. So on these motors, one thing about them, one thing I love about these things that we can't do with PSCs as effectively is design them for the appropriate static pressure. So now my PSC design is essentially used for both condensers and for blowers. But on ECs, I can design it more specifically if it's being used with a fan blade or if it's being used with a blower. Well, why is that? Because they react differently to the static pressure. And so now we can design them and take into account what's going to happen to them as we put them in a load, whether they're used in a fan or in a blower. So when they're used with fan, typically we design them as what we call a constant speed. But when we use them with blowers, we can even get more refined on them. And we can design them when my furnace has a bunch of bells and whistles and gives me a lot of capability, a lot of high efficiency ratings in that equipment, or something that is more basic. So we can design them as the constant airflow or the constant torque. Did anybody attend Chris's class on ECs? Yeah. And I'll bet you he talked about these motors being designed for these different applications. That's why they're designed like that. Now, when I have a constant speed motor, the fan blade's going to react the same way to my load. It's going to react the same way to the static pressure. So that fan, as I increase static, I have more load. But that motor now will increase its torque so that my speed remains the same on that. That doesn't happen with a PSC. But the load on the fan reacts the same to the static pressure, whether I've got an EC or a PSC on there. But the motor can react a little bit differently. Now with the blower, remember that blower operates a little bit differently. It reacts differently to the static pressure. But that blower, it doesn't matter whether it's equipped with an EC or a PSC, the load on that blower reacts the same way to the static pressure. And as I increase my static and I restrict the amount of air that I have, it removes load. But if I reduce my static pressure, I have more load. I don't have as much restriction of air. So the devices themselves, the fans or the blowers, are going to react the same way, but the motors are going to react a little bit differently. Now, when we look at this, this is showing on that red line, and you probably saw in Chris's presentation, a constant airflow. And it's comparing the air of a constant airflow equipped blower. So in this case, if it's designed for 1200 CFM, we'll see that as my static changes, even though the load on that motor is going to change by the static, the motor reacts in order to maintain the same amount of air by increasing its speed as I have the restriction in that air. Whereas with a PSC, we can see that that will decline. Comparing the PSC to a constant torque, an X13, they look a little more similar to what we see on that curve of the constant airflow, but they do a better job in terms of maintaining air than what a PSC does. How many have heard that if I have a bad static condition, put an EC in there? Who's heard that? Yeah. So you guys who attended Chris's class yesterday, what did Chris say about that? That's hogwash, isn't it? No, that's not going to happen. So I have the same restrictions. One of the reasons for the same restrictions, that static pressure is the load on that. These motors are air over motors. They're designed to have a certain amount of air on them. So we can't correct a bad static condition by putting an EC in there. What do you have to do to correct it? Ductwork, yeah. Or have Eric come in. Eric can fix anything. So you have to correct that static condition. You can't put a different motor in there. You can't put a larger horsepower motor in there if you have a static condition, a bad static condition. So if you think that a larger horsepower is going to give you more air, that motor is going to fail prematurely. So I think that what I want everybody to leave with is just a better understanding that there is a difference between the reaction of a fan blade and the reaction of a blower when it comes to changes in static pressure. But it's easy to overlook that. And as a technician, if you see dirty filters, your first thought is that your amps are going to be high. And that's not the case. The motor's going to fail, and your capacitor is going to fail, but it's not because it's overloaded. It's actually underloaded and not getting the proper amount of air. So with all of these motors, whether they be ECs, whether they be PSCs, whether they be shaded pole motors, we want these motors to be operated in the load situation they're designed for. And that load is air and the static pressure that we see. Well, we've got a website you guys can go to. We've got some training videos on there. If you're interested in those, feel free to access that for us. So that's our website. Questions? Yes.
So on a PSC blower, if the filter's plugged up, the amps will go down. But if the coil's plugged up, will the amps also?
Yes. And when we look at static pressure, that static pressure is on both sides of that blower. So we have static pressure on the inlet side, we have static pressure on the outlet side. The total static is taking my inlet side, which is a negative static pressure, changing the sign of that, and adding it to the positive static pressure on the outlet side. That would be the total static. That's a good question. Thanks for bringing that up.
The amps, as a PSCs, the load is less than the amps drop. On the ECM, the load is less than the amps go up. Is that correct?
It depends upon the EC. So with my constant speed, I would see that as I add static, more load on it, but I'm providing more torque, my amps go up. On my constant airflow, as that motor becomes unloaded, that motor is going to produce a higher speed. I'm going to increase speed. My amps will go up on that. So it depends on what we look at. That's a wrap. Okay. Appreciate you guys.
Thanks for watching this video. Again, to find out everything we have going on, you can download the free HVAC School app on Android or on iPhone, or go to HVACRschool.com. And then specifically up in the top, you'll see events to find out more about upcoming symposiums. Hope to see you there.
Thanks for watching our video. If you enjoyed it and got something out of it, if you wouldn't mind hitting the thumbs up button to like the video, subscribe to the channel, and click the notifications bell to be notified when new videos come out. HVAC School is far more than a YouTube channel. You can find out more by going to HVACRschool.com, which is our website and hub for all of our content, including tech tips, videos, podcasts, and so much more. You can also subscribe to the podcast on any podcast app of your choosing. You can also join our Facebook group if you want to weigh in on the conversation yourself. Thanks again for watching.